In this video, we're going to talk about phenol. We'll go through the reactivity of phenol and the reactions of phenol, going on to directing groups of phenol and other important directing groups to do with benzene and its reactions. So first of all, functional group is phenol. Now, it's really important this. When I'm talking about phenol, phenol is the functional group, and it's a benzene with an alcohol group directly attached. Now, the functional group is not benzene, it's not alcohol, it is phenol. It's the most common thing I see when it comes to exam questions. So it's really important. So if we go across and we look at it, we can see that there is phenol here. We've got the OH connected to the benzene. Remember, the benzene can be 3 double bonds alternating around this ring as well. Now, if we're talking about the important aspects and properties of phenol, one is solubility. So it is soluble in water, okay, but it's more soluble in alcohols. And the reason why is to do with hydrogen bonding, okay? It can hydrogen bond. So because it can hydrogen bond, it can form hydrogen bonds with water. So let's draw a hydrogen bond. And if you're watching, try drawing a hydrogen bond first. Okay, so if we look here, here's the water. First thing we do with a hydrogen bond is draw the dipoles on everything. So I've got my dipoles on my phenol. I've got my dipoles on my water. Then I draw my lone pair and my hydrogen bond. And you can see the hydrogen bond just coming out over here and across. And that is why the solubility of phenol is good in water, but even better in alcohols because it hydrogen bonds more strongly to alcohols. We're now going to go on to talk about the acidity of phenol when you compare it to alcohols and carboxylic acids. Now, this depends on the stability of the conjugate base. So the conjugate base is what happens when the acid loses a proton. But first of all, let's talk about the trend. So we're going to talk about the trend going from the alcohol to the carboxylic acid. We know that the pH decreases as you go from alcohol to phenol to the carboxylic acid. Now also we know the acidity increases. So that means if the pH is decreasing, the acidity is increasing. Now what we have here is a general formula of a carboxylic acid. And what happens in a reversible reaction, an equilibrium, you will lose that proton. When you lose that proton, you have a lone pair of electrons here, and that lone pair of electrons causes this to have an extra electron in total, and therefore a negative charge. But that negative charge, highly unstable, wants to react with the H plus and then go back. So there's a reason why, though, that it's a bit more stable than you would expect, and we'll talk about that now. So imagine you have that lone pair of electrons, but instead that lone pair of electrons is delocalized across these 3 atoms. Imagine a bit like this, and the lone pair of electrons is going across the carbon to the other oxygen and back and forth and back and forth. And it's not going as a pair, it's going as singles, back and forth, back and forth. Now, if that's going back and forth, that means there's less repulsion, and therefore the negative charge is spread over 3 atoms as well. If that's the case, less repulsion, much more stable, in equilibrium, is going to the right. If the equilibrium is to the right, I produce lots of H plus ions, and therefore I have a low pH. More H pluses you have in solution, the lower the pH is, and the more acidic. If we look at phenol, we have a delocalized system with pi bonds above and below the ion, and you can see there that they're moving around above and below. So that's a lot of electrons, that's 8 electrons in there, and 8 electrons moving around this ion. Now that means they're delocalized and they're spread out, but it is slightly less stable than the one above. It's still stable, but it's slightly less stable than the one above, which means the equilibrium is slightly less to the right, okay? So if the equilibrium is slightly less, you can see I've drawn a tinier arrow here, okay, just because this is not quite as stable as this. Now if we go for the alcohol, we can see that there's no delocalization at all. So the negative charge is kept on here. And what that's known is it's localized, it's not moved, it's not delocalized like this, it's not delocalized like this. And therefore, the lone pair of electrons that would be on the oxygen to cause the minus suffers more repulsion, not less. And so it's not stable. So what it does, it reacts a lot with this H+, which means the equilibrium is over to the left, and therefore you get more of the alcohol and less of the H+, and therefore it's not very acidic at all. Let's talk about the reactions of phenol. So you can react them with an alkali, which is soluble base, produces hydroxide ions. Okay, and you can do it like this. So you can have this phenol written like this, C6H5 as well, and this is a kind of phenoxide ion, it's called C6H5O-, with the Na+ where the oxygen is. Now this Na+ is actually ionically bonded to the O-, and therefore this is soluble in water. And that's a really good kind of point, is that if something has ionic bonds, it is more soluble in water than it would be without ionic bonds. So, and also the melting point is higher. So the melting point of this will be higher than the melting point of this because we have an ionic bond, and ionic bonds are very, very strong. Now let's draw this in skeletal formula. And you can see that there is this ONA that we have here. Haven't drawn the minus and the plus. You don't always have to draw the minus and the plus. Okay, but we must recognise that it is an ionic bond. Now, our exam tip here, okay, is multiple choice questions can often ask whether the reaction is or is not redox, neutralisation, disproportionation, etc. So you have to know what type of reaction this is. So if we're looking at this, we can see that phenol is slightly acidic. Okay, so therefore we can term it as an acid. We know that this is an alkali. Because this is an alkali, we've created an acid plus alkali, salt plus water. So we've created water. So one of the rules for neutralisation is that you have an acid plus an alkali, and you often produce water. So because this is producing water, we call it neutralisation. And that may come up in a multiple choice question at some point. Now, it can also react just with the metal and not the alkali. Now you notice it creates the same thing, this sodium phenoxide, the phenoxide ion, the sodium, and it's got this ionic bond again. But this time it's an acid plus a metal goes to a salt plus hydrogen. Again, if we draw it in skeletal formula, you can see that we have our ONA, ionic bond again, higher melting point, increased solubility in water, and you have the hydrogen. Now, that means you're going to see a gas. And so one of the questions they can slip in, usually in AS and things like that, is what do you see in the reaction? So if you know a reaction like this, you can see that the hydrogen, okay, is appearing, so that's gas appearing, and the metal is reacting and disappearing. Not often asked in A2, but might be asked if you're one of the few people in the country who are doing an AS examination. Now let's start to compare the reactions. So ethanol is a weak acid, so it doesn't react with sodium hydroxide. Phenol is a stronger acid, as is carboxylic acid, so they do react with strong bases such as sodium hydroxide. But this is the really, really important thing. Only carboxylic acids react with weak bases such as sodium carbonate. And in A2, they will ask you questions about phenol or carboxylic acids or carboxylic acids and try to differentiate them. So for example, if I'm talking about a carboxylic acid, how would I identify it versus a phenol? So if I had a phenol and a carboxylic acid, I would add sodium carbonate. It's sodium carbonate, I would get gas released and I would see that bubbling. We'll talk about that in a bit more detail in other videos. But we wouldn't see phenol bubbling. It wouldn't react with the sodium carbonate. So really important, this doesn't react with sodium carbonate, but the carboxylic acids do. Now let's talk about the reactivity of phenol with bromine. A phenol reacts with bromine and creates this tribromo compound. And this tribromo compound is 2, 4, 6. So you see it's at 2, 4 and 6. So if that's 1, this would be 2, this would be 4 and this would be 6. And every single time it reacts, it creates HBr. So we've got HBr here. For every one of those, there will be 1 HBr. And this is substitution, because what's happening is when the Br comes in, there's a H here, which we haven't written because it's skeletal, and the Br swaps for that H. And then the H then bonds with the remaining Br. You don't need to know the mechanism of how this works, which is why I haven't gone over the mechanism at all. But really important, if there's 1 bromine and there's 1 HBr for every time you do the substitution, okay, that means that I'm going to have 3 Br2 and 3 HBr, because I'm doing this 3 times. So I've done it here, I've done it here, and I've done it here. So remember, the bromines react with phenol in the 2 or 4 or 6 positions. Only place the bromines on if these positions have hydrogen on them. So I talked to you here about the bromine reacting in the 2, 4, 6 position. But if there's not bromine on there, there's something else, don't react it. So let's go through an example of that and use our exam tip. So here we have phenol and we have an amine group on position number 2. And because there's an amine group on position number 2, I'm not going to do this substitution. And this is really electrophilic substitution. So that electrophile is not going to come on to that carbon. So that's on position number 2, so that's filled. We could go 2, 4 or 6 positions. We only go on the positions where there is hydrogen. There is no hydrogen there. So I'd like you to predict and have a look there and say, what do you think that will produce? What do you think the full equation would be? So the full equation is going to be plus Br2, and then we're going to create our compound. Notice with our compound here, we haven't put it in 2 because there's not a H there, there's just an NH2. We put it in 4 and we put it in 6. Now the next thing is we need to balance it all out. So how many bromines have we actually added? We've added 2 bromines. That means we need 2 Br2 and we need 2 HBr. And that is how you react bromine with phenol. And what the other thing to mention is that it reacts without a halogen carrier. So it reacts quite easily without a halogen carrier. If you've done the benzene video, you notice that benzene needs a halogen carrier to make it work. This does not need a halogen carrier. The electrophilic substitution just works very well at room temperature and creates you a multi-brominated or halogenated compound. You do need to, though, remember this structure. And you do, therefore, need to know what if the position 2 or the position 6 or 4 is filled. What do I do? And just remember our exam tip. It reacts at 2, 4 or 6, but only if the position has a hydrogen on it. If it has another group on it, you don't do the reaction. The next step is to talk about the reactivity of alkenes versus benzene and phenol. Before we do that, it's good to remind us of the electrophilic addition mechanism that happens when you add bromine to cyclohexene. So I've drawn here the pi bond above and below the bond here. And that pi bond is full of 2 electrons, and those 2 electrons are localized. And they're localized, which means that as a bromine molecule approaches here, the electrons get repelled by these 2 electrons that are localized. The negative's stuck in position, so it creates a very strong negative charge that repels these 2 electrons and they go towards the bromine. Because of that, you induce a dipole, and the dipole then creates your electrophile here. So your electrophile, and that means the electrons in the bond are then attracted to the bromine, And then there's too many bonds to the bromine, so there should be one bond to each bromine. There's too many, so one of the bonds has to break. So these electrons have to go onto the bromine to break the bond, so this bromine has the right number of bonds. And that creates a Br minus, but hopefully you've done this mechanism before, and that's just a reminder. Now this means there is polarization going on. So this is this polarization to make this delta plus and this delta minus. Now how do you answer the question about the reactivity then? So whether this is more reactive with cyclohexene, the alkene, or is benzene more reactive, or is phenol? Well, the first thing you need to do is split it into three sections. Delocalized or localized. So look at your example and choose whether the electrons within the reaction are delocalized or localized. You then have to look at the electron density. Is it high or is it low? So this is the electron density of the electrons within the molecule that's reacting. So in this case, it would be this pair of electrons here. In phenol, it would be the electrons in phenol, and in benzene, it would be the electrons in benzene. The last one is polarizing. Is this polarizing? Is the alkene polarizing enough to make this reaction happen, or is the benzene, or is the phenol? So let's start with this example of the alkene. Well, first of all, those electrons are stuck in position, therefore they're localized. Because they're stuck in position, they have a lot of electrons in a very small space. Therefore, the electron density is high. And because of that, they polarize this bond, and that's why we showed the mechanism. So if you're in the exam, and this is an exam-style question, very, very common, you need to be good at it, okay? So just mention in the question, in cyclohexene or any other alkene for that matter, the electrons are localized, they're of a high electron density, and they're polarizing. And that will get you at least a couple of marks out of the question. Now the rest of the marks come from whether they compare phenol or benzene to cyclohexene or another alkene. So let's talk about benzene. Now we know with benzene that the electrons, okay, are delocalized and they're going around above and below the plane, and they're pi bonds. And now we also know that there are 2 electrons per pi bond. There's 3 pi bonds, so 3 times 2, so 6 electrons. So those 6 electrons we draw here are all going around in a circle. So 3 up there and 3 up there. So they're very far apart. You see a big gap in between the 2 here. So if there's a big gap, that means they're not with their original atoms. Remember, they're not with their original atoms. They're flowing around. These are with their original atoms. Okay, they're delocalized. If they're delocalized, and they're spread apart, the electron density is low. And we know from our reactions with benzene, we know that benzene does not react unless you have a halogen carrier. So therefore it can't be polarizing, because the halogen carrier, which is usually aluminium bromide in this case, or aluminium chloride if you're doing chlorination, okay? So it needs a halogen carrier, it's not polarizing. Let's look at phenol. So in phenol, we have the lone pairs of electrons that are here and here. So those lone pairs of electrons get involved in the delocalized system. So they will create the delocalizer system here, and you see it's like a 10-pin bowling pin, okay? And that goes around in that shape. And that means they're spread all around this area, which means they are delocalized, okay? So they're delocalized, and there's lots and lots of electrons in there, including those 2 electrons, including the original ones in the benzene. But you must say that the lone pairs of electrons delocalize into the ring. So you must say they delocalize into the ring. Avoid using any other words other than that. I'm not going to say what words I see in the exam, because I'm just going to reinforce that to you. Make sure you say lone pairs of electrons delocalize into the ring, nothing else. So they delocalize into the ring. Now because that happens, you've got a lot more electrons in that space. So because of more electrons in that space, it's a high electron density, not low. You'd think it was a low because of the delocalization, but you've actually got more electrons in there, so they fill the spaces. So because they fill the spaces, it's a high electron density. Now, we know that phenol reacts readily with bromine, and it does it 3 times at the 2, 4, or 6 position. So it is polarizing. Now, let's look at an extra complication. An extra complication is if it's electrophilic substitution of phenols, it can sometimes be polarization or attraction. And I'm only putting this in as a really difficult area which comes up, because it comes up every now and again and it throws people. So here we have our normal bromination of phenol. Bromination of phenol is polarization, polarizing that bromine because of the high electron density, because it's delocalized electrons, high electron density, the oxygen is donating its electrons into that ring. Okay, and something really interesting to say, this happens the same with other molecules such as phenylamine and things like that, which have NH2s there because they also have a lone pair of electrons. But with phenol, polarizes readily, okay, definitely polarization. But if we did it with a nitration, okay, and we nitrated phenol, it wouldn't be polarization, it would be attraction. And that's because the electrophile that's produced is NO2+. So what I'm saying to you is if you come into an exam and the reaction with phenol has a positively charged electrophile, then you're not going to polarize something that's positively charged already. You're going to attract it. So it's the high electron density that attracts the nitro group. So our example here is phenol reacting with HNO3 aqueous or dilute HNO3. Now, let's compare that to benzene. Normally, if you did benzene and you were nitrating it, you need concentrated HNO3, concentrated H2SO4. You don't need concentrated H2SO4 or HNO3 in this one. You just need a dilute, and that's an easy way for them to catch it out. Now remember, you can do dilute by putting an AQ by HNO3, or you can do it by just calling it dilute HNO3. But either way, dilute HNO3 or HNO3 aqueous must be used if you're nitrating phenol. Now we'll talk about this slightly later in the video in more detail, but the NO2 plus goes in specific positions. So it will go in either the 2 position, so if you look here, this is 1, 2, or it will go in the 4 position. So 1, 2, 3, 4. Okay, so that means the OH will direct into the 2 or 4 position, make something react in the 2 or 4 position. And so you'll get a mixture of products if you nitrate phenol. And remember, the mechanism will be to do with attraction, not polarization. If it's bromine, it's polarization. If it's this, it's attraction. So in the previous example, we have started to talk about directing groups in position 2 or 4. But let's now go into a more complicated complex description of directing groups. Now when an electrophile reacts with benzene, it will bond in the 2, 3 or 4 position depending on the group already attached. Okay, and that group already attached is called the directing group. In the previous example, the directing group would have been OH because it was already on the benzene, okay? So if you look at it here, this would be 1, 2, 3, 4. So this would be the OH has directed the NO2 when it reacted with it into the 4 position. So you need to get used to just labeling the 1, 2, 3, 4, 5 and 6. Positions in benzene. But remember, the 5 and the 6 are essentially positions 2 and 3 in times of directing. And that's why when you get bromination of phenol, you get bromination of 2, 4 and 6, because 2 and 6 are essentially 2. They're still 1 away from the OH. Now, the good thing is you will not be expected to know any more groups other than the ones I described to you in the next few slides. But you may be asked to do a directing group question if given certain data, and we'll go through that. So, the first directing groups that you need to know are OH and NH2. And they are 2 or 4 directing, but hopefully you know that because we've done nitration of phenol and it was 2 or 4 directing. And important thing is they're electron donating. So you must associate electron donating with 2 or 4 directing. So if we look at an example, there is our directing group, OH, it's already on there, okay, and it's electron donating. If we then react this, and as we did in the previous slide, dilute HNO3, we get the position number 2, okay, and then we get position number 4. So if you see a phenol and it reacts with, in this case, dilute HNO3, but it can be any other electrophile essentially, because you do electrophilic substitution with this, you'll see that it goes in 2 or 4. So we're going to finish our video on an exam-style directing groups question. The directing effects of different groups attached to a benzene ring are shown in this table. So you can see in this table I've got a list of groups and I've got where the new substituent is directed. Where is it going to react? So it's going to react to these different positions according to the group. And then we're asked to give the products of the following reactions. So I've got a CN group and it's reacting with aluminium chloride, and I've got a phenylamine, an NH2 group, acting with chlorine. Really good thing is, notice this does not have a halogen carrier and this does, and that's because this is just as good at reacting as phenol, but we'll talk about that in a bit of detail next. For now, let's move this over and then we can start to go through the question. First question is CN. I go across and I have a look, and CN is directing to number 3. That means my chlorine, which is going to be joined on because this is aluminium chloride, is going to go at position number 3. So again, it's position number 3, and that's the simplest kind of question that you will get. This one, okay, is an NH2. So, as I mentioned earlier, it's got a lone pair of electrons here, which is just the same as an OH, and therefore you don't need the halogen carrier. This lone pair of electrons donates into the delocalized system, gives it a high electron density, which means it polarizes chlorine without the need for a halogen carrier, and that again is a complication they can put in some questions. Now, if that is the case, this is why this is really quite difficult. The NH2 is 2 or 4 directing, so it's 2 or 4 directing, but remember 2, 4 can also be 6, so let's put that in a bit more context. So this is position number 2, this is 4. But if you start and go the other way around, this is still position number 2. So this is position number 2 here, which means that you'll get 3 chlorines reacting, and they're all in the 2 or the 4 positions. One there, and one there. So it's a complication on this kind of question that can easily throw you. But if something is reacting in 2 or 4 positions and it's fully reacting, because this is, for example, would happen with phenol or with something else like phenylamine that has a lone pair of electrons, which is delocalized, which is polarizing, okay, you potentially get all 3 positions filled. That's a really important thing to know to get those highest grades.